You can spend $600 building a backyard aquaponic system and ruin it the moment it looks finished. The tank is full. The pump is humming. Water is splashing back through the pipe. The grow bed is packed with gravel. From 10 feet away, it looks like the dream. Fish below, vegetables above, one loop turning waste into food. So the homeowner does the obvious thing. They add fish. That is where the system can start failing. Because fish do not care that the plumbing works. They care whether the water can process waste. And in a brand new system, that invisible living filter usually is not ready. No mature bacteria, no stable cycle. Ammonia with nowhere useful to go. Nitrite rising before the loop can carry it. Uneaten feed softening in the corners. Water that looked clean yesterday starting to turn against the tank today. Aquaponics is powerful because it can turn waste into vegetables and protein. But build it too fast, and you do not get a food machine. You get expensive water that cannot protect the fish. Before the first fish goes in, the real question is not whether the pump runs. It is whether the water is alive enough to carry the loop. The idea behind aquaponics is older than the parts used to build it. Long before food-safe totes, submersible pumps, and PVC fittings, people had already learned that water, plants, fish, mud, insects, algae, and nutrients could become stronger when they were connected instead of separated. You can see the same principle in older wetland food systems. Canals beside growing beds, pond mud returning to fields, fish living inside productive water instead of outside the farm. In some places, fish ponds were tied to trees, insects, crops, or livestock so that one output kept moving into the next use. Those systems were not backyard aquaponics. They were larger, local, climate-shaped, and built around different species, different tools, and different rules. A 300-gallon tank behind a garage is not an ancient lake system, and a plastic IBC tote is not a traditional pond landscape. But the deeper principle survives the change in scale. One output can become another input if the right living process sits between them. That principle is what modern backyards often lose. Most yards are arranged as separate zones. The lawn is one thing. The raised bed is another. The hose is on the wall. Fertilizer sits in the garage. Fish, if they exist at all, live in a pond or aquarium separate from food production. Everything has its own product, its own bag, its own bottle, its own replacement cycle. Aquaponics asks one corner of the yard to behave differently. It does not treat fish waste and plant fertility as two separate problems. It asks whether those problems can be connected through biology. That is why the system rarely fits neatly into the normal backyard shopping path. You can buy the pieces in a weekend, but you cannot buy the mature loop. The useful part is not sitting on a shelf as one finished product. The useful part is the relationship between fish load, water chemistry, bacteria, roots, oxygen, pH, electricity, and time. This is also why aquaponics is easy to oversell. The big promise is not completely fake. A mature system really can make water, nutrients, fish, and plants work together in a way most backyards never do. It can produce greens. It can raise fish under the right conditions. It can make each gallon of water do more work before it leaves the system. But the promise becomes dangerous when people talk about the harvest before they talk about the living filter. The simple explanation people repeat is that fish feed the plants and plants clean the water. That is close enough to create curiosity, but not close enough to build the system safely. The fish do not feed the plants directly. Fish waste creates ammonia. Some ammonia comes through the gills. Some comes from solid waste. More comes from feed that the fish do not eat quickly enough. Those pellets soften, sink, break apart, and collect in slow corners of the tank. In a normal fish tank, ammonia is a problem to control. In aquaponics, ammonia is the beginning of the loop, but only if bacteria are ready to handle it. Nitrifying bacteria colonize wet, oxygenated surfaces. They are the living bridge between fish and plants. One group of bacteria moves ammonia toward nitrite. That is progress, but nitrite is still dangerous for fish. Then other nitrifying bacteria move nitrite toward nitrate, which plants can use more easily. The chain is simple to draw. Fish create ammonia. Bacteria convert ammonia into nitrite. More bacteria convert nitrite into nitrate. Plant roots take up part of the nitrate, and water returns to the fish tank. The filter is not one magic device, it is the whole wet path. In a media bed system, the grow bed is not only holding plants. The gravel or expanded clay becomes bacterial real estate. Every pebble adds surface area. Every flood cycle brings waste and oxygen across those surfaces. The bed becomes a biological workspace, not just a container for lettuce. This is why a new system cannot be rushed. The hardware can look finished before the system is ready. A tank, a bed, and a pump can move water without creating a living filter. Fish can be added before the bacteria are strong enough. Feed can enter before the loop has a place to send the waste. That is when aquaponics turns against the beginner. The same waste that should eventually feed the system starts building up faster than the system can process it. The water may cloud. The smell may sharpen. Fish may feed less aggressively or hang near the surface if oxygen is low. Roots may look brown, weak, or slimy instead of pale and firm. A beginner may blame the fish, the pump, the plant variety, or the whole idea of aquaponics. Very often, the real problem is simpler. The visible build was finished, but the invisible filter was not. The most important early numbers are not harvest numbers. They are water numbers. For many small aquaponic systems, pH often sits near a compromise range around 6.8 to 7.2. Some systems can work a little wider, but the point is not to chase a perfect number every hour. The point is to avoid invisible drift. Fish, plants, and bacteria do not all prefer exactly the same water, so the homeowner is managing a workable middle. pH also changes risk. The same ammonia reading can become more dangerous when pH and temperature rise. That means pH is not just a color on a chart. It changes how much danger the tank is carrying. During cycling, ammonia and nitrite may appear because the bacterial colony is still forming. That does not automatically mean the system is failing. It means the loop is still under construction. Before adding a real fish load, the system should show a pattern. Ammonia can fall, nitrite can fall, and nitrate can appear. That pattern is the first proof. Not a basket of lettuce. Not a big fish harvest. Not a thumbnail full of food. The first proof is water that begins to make sense. Write the numbers down: date, pH, ammonia, nitrite, nitrate, water temperature if possible, and notes on clarity, smell, pump flow, roots, and fish behavior. A notebook makes the system less mysterious because it connects what the test kit shows with what the eyes can see. In the first month, the work is not harvesting. It is restraint. Feed less than you want to, test more often than feels necessary, and give the living filter time to become strong enough for fish. Do not start with a farm-scale fantasy. Start with a system a normal homeowner can watch closely. A 300-gallon tank or food-safe IBC tote is a practical learning scale. It is large enough to show the loop working, but small enough to manage before mistakes become expensive. Pair it with a grow bed around 4 feet by 8 feet, filled with washed, expanded clay or clean gravel suited for aquaponics. The small version has to pass 3 gates before fish enter. The first gate is the site. A full 300-gallon tank is heavy, so it needs level, compacted ground, pavers, or a base that can handle the load. Avoid a soft corner that puddles after rain. Keep the system close enough to power for the pump, but use outdoor-rated electrical protection and keep cords away from standing water. Also think about where overflow or leaks would go. Water returning toward the house foundation is not a small detail. The second gate is flow. Run plain dechlorinated water through the system before adding fish or ammonia. Watch how the water enters the bed. It should spread through the media, not cut one channel and bypass half the root zone. The return should land back in the tank without splashing out. The pump should sound steady. The bulkhead should not drip. Any pipe that may clog later should be removable, because roots, algae, and solids do not care how clean the plumbing looked on day one. A union fitting or removable section of pipe can save the system later when flow starts slowing down. The third gate is biology. Start the system without fish, add a proper ammonia source, and test until the pattern from earlier appears. Ammonia can fall, nitrite can fall, and nitrate becomes measurable. Fishless cycling is safer for beginners because no fish have to live through the unstable ammonia and nitrite period. Do not use household ammonia with soap, scent, or additives. Many new systems need something like 2 to 4 weeks or longer before the water pattern begins to stabilize, depending on temperature, oxygen, chlorine, pH, surface area, and how the system was started. That waiting period feels like delay. It is actually the build. When fish finally enter, stock lightly. A beginner stocking plan is often discussed around 1 pound of fish harvest weight per 8 to 10 gallons of water, but that should be treated as a planning ceiling, not a day one invitation. A new system deserves margin. Fish species are local. Tilapia are common in aquaponics discussions because they grow well in warm water, but they may be restricted in some places and do not fit cold outdoor systems without heat. Catfish, bluegill, or other legal edible species may fit different climates and goals. Goldfish can work for a learning or ornamental system, but they do not serve the protein side of the promise. Before buying fish, check state rules, local ordinances, and HOA limits. Materials matter too. A cheap, unknown tote is not automatically a bargain. If the container held something you would not want near food or fish, do not use it. Be careful with treated lumber, questionable liners, galvanized metal in the wrong place, and cheap fittings that may fail under constant water. Start with crops that answer quickly: lettuce, basil, kale, pak choi, and many herbs make better starter crops than tomatoes or peppers. They do not prove the system can feed a family. They show whether the water loop is beginning to feed plants. Use greens as an early dashboard. Pale new leaves can point toward nutrient availability or pH trouble. Slow growth after cycling can point toward low nutrient levels, poor light, or weak flow. Brown or slimy roots can point toward oxygen problems. Algae on the media can mean the flood level is too high, or the top layer is staying wet and exposed. Keep the flood level below the top of the media. A dry top layer helps reduce algae and fungus gnats. Fruiting crops can come later. Tomatoes, peppers, cucumbers, and strawberries ask more from the system. They need more nutrients, stronger balance, and a more mature loop. If they go in too early, they may survive without proving much. The first goal is not maximum yield. The first goal is stability. Once the system matures, it can feel almost like it is feeding itself. Waste moves, bacteria work, roots respond, and water returns. Feed becomes fish growth, plant growth, and biological activity instead of disappearing into separate systems. But that feeling is earned. There are still inputs. Fish feed matters. Electricity matters. Water top-offs matter. Test kits matter. Replacement parts matter. In some climates, temperature control matters. Some systems also need small mineral corrections over time, especially iron, potassium, or calcium, depending on crop choice and water chemistry. The promise is not zero input. The promise is that more of each input starts doing more than one job. Aquaponics looks automatic from a distance. Up close, it is a routine of small checks. If the pump stops, oxygen drops and water stops carrying waste to the bacterial surfaces. If the power goes out, do not feed. Feeding adds waste when the system has the least ability to process it. A small battery air pump can buy time by keeping oxygen moving. If dissolved oxygen gets low, fish may stay near the surface, feed weakly, or move slowly. Warm weather makes this more important because warm water holds less oxygen. More surface movement or an air stone can matter more than adding another plant. If the siphon fails, the bed may stay too wet or drain poorly. Check the standpipe height, bell cover, media guard, and flow rate. Sometimes the fix is as simple as adjusting the ball valve so the inflow matches the siphon's working range. If roots turn brown, weak, or slimy, look at oxygen and flow before blaming the seedling. Healthy roots should look firm, not mushy. The bed should smell like wet stone and roots, not sour water. Some limits are not repair jobs. They are fit questions. A system that works in a warm climate may not fit an exposed cold yard without heating. A fish species that works in one state may be restricted in another. A setup that produces extra greens does not automatically become a business. Selling food can involve handling rules, labeling, local permits, inspections, and market demand. A pilot system should prove stability before it tries to prove income. That is not a weakness. That is what makes the system real. The payoff comes in stages. In the first week, the win is clean flow, no leaks, no stalled drain, no dead corner where solids collect, and no water running where it should not go. During cycling, the first real signal is not plant growth. It is a pattern in the test tubes. Ammonia does not keep climbing. Nitrite does not stay high. Nitrate appears. pH stays in a workable band. When greens go in, the win is steady new growth. Lettuce, basil, kale, or pak choi begin to show whether the water loop is feeding plants instead of simply moving around the yard. When fish go in, the win is restraint. A light fish load, steady oxygen, and feed that disappears because fish are eating it, not because it is dissolving in the bottom corner. Later, if readings stay stable, the system can carry more plants. A more confident fish load, maybe fruiting crops, maybe extra greens beyond the household's first needs. A mature backyard aquaponic system can become a real food buffer. It can produce fast greens. It can raise fish under the right conditions. It can reduce some purchased plant fertilizer. It can use water efficiently because the same gallons keep circulating instead of running off. But it should not be sold as a complete grocery replacement. A 300-gallon tank behind a garage is a learning system, a small protein and produce loop, and a useful layer of resilience. That is enough. In fact, that is why it is believable enough to start. End at the tank rim. The water is moving through the grow bed. The return line is dropping back into the tank. A few greens are growing above the media. The fish load is still light. The test tubes are lined up where a staged harvest basket would look better on camera. But the test tubes are the honest proof. The ammonia tube is not screaming danger. The nitrite tube is not stuck high. The nitrate tube shows the loop is processing waste. The pH is still in a workable band. At the beginning, this was only water moving through hardware. Now it is water carrying information. The system has not replaced the grocery store. It has done something more useful for a real backyard. It has become readable. And once a homeowner can read the loop, they can keep it alive, adjust it, grow it slowly, and let one corner of the yard start doing what most corners never do. Turn waste into input, turn water into a carrier of fertility, and turn a fish tank with a grow bed into one small food system. That is where backyard aquaponics actually begins. Not with the first fish, not with the first lettuce, not with the first big promise, with water that can finally carry the loop. For more overlooked backyard systems broken down this way, the mechanism, the small version, the failure points, and the realistic payoffs, subscribe before the next one. The next system only matters if it can survive contact with a real yard.